Hello students, in today's class we'll be learning how to decide the shape of a molecule, electron domain of a molecule. This is a very important question and a question which comes quite often in your ASA level exams, IBDP board exams. So this topic, let's do it together. But before we start, this will require some knowledge of to be able to draw those dot and cross structure for covalent compounds. So if you're not confident in those, I'll drop a link for that video also. It's a 20-minute video. You can just watch it and you can just learn how to draw the dot and cross structures and then come back here and start learning the shape of the molecules. Okay. So let's start without doing any delay. We are going to talk about how to decide the shape of a molecule, shape of a covalent molecule. Okay. And it's going to be a very interesting topic, and it's a very important topic as well. So you have to be very focused. This is decided by a theory called VSEPR theory. VSEPR theory. And VSEPR theory stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory is what is called VSEPR theory, and that decides the shape of a molecule. Okay. So what does that say? It says that the electron pair, the electron pair around the central atom tries to adjust itself in such a way, the electron pair around the central atom tries to adjust itself in such a way so as to minimize the repulsion between them. Okay. Electron pairs around the central atom will always try to adjust themselves in such a way so as to minimize the repulsions between them. Okay. And electron pairs are what? We are talking about lone pairs. We are talking about bond pairs for the bonds around the central atom. Okay. So electron pairs can be what? Electrons pair can either be lone pair, the non-bonded electrons, or the bond pair, which are the bonded electrons. And strength of repulsion, if we talk about the strength of repulsion, like which kind of electron pair repel more and which repel less. And then that's very important to know because lone pair repulsion. That means one lone pair repels the other lone pair much strongly than lone pair, bond pair, and then bond pair, bond pair. Okay. So this you have to take care of. So if any structure, when we are trying to draw the shape of it, we'll try to keep the lone pair as far as possible because that way we'll be able to minimize the repulsion. Correct? So lone pair and lone pair should be kept as far as possible. Bond pair and bond pair, they don't repel each other. We can keep them as close to each other and it won't be an issue. Okay. Yeah. So that these are the points which you have to take care of. Now, what we'll do is one by one, we'll talk about examples and see how to decide the shape. Okay. Let's go. The first compound that we are going to do is beryllium chloride, BeCl2. Okay. Beryllium chloride. Now, how to draw the structure, the dot and cross structure. As I've told, there's another lecture for it. 20 minutes of a lecture. You can just go through it and learn how to draw all of these structures we have discussed there. It is going to look like this. It is going to be a beryllium, and then there will be two chlorines bonded to it, and then there will be lone pairs on fluorine, which we don't care about. This is our central atom here. This is the central atom, and it has what? Two bond pairs, zero lone pairs, right? So we have a total of just two electron pairs, which are two bond pairs. We just have two bond pairs. So what is the best way of keeping these two bond pairs so that the repulsion between them is minimized? That's 180 degrees, right? So if we keep them like this, see, I'm drawing it here, beryllium in the center, then we have chlorine, then we have chlorine, beryllium, and chlorine. The angles between them are 180 degrees, right? Like we can draw it here as well. Beryllium in the center and chlorine at 180 degree. Why we are keeping it at 180 degrees? To have maximum separation between the two bond pairs, right? Or the two electron pairs. This is correct. But if we draw something like this, it would be wrong because see, the separation is not good. It's like they are close to each other, which is not needed, correct? So it is linear shape. So we'll say that PeCl2 is linear in shape. Okay. PeCl2 is linear in shape, and that is how we are going to decide. The idea is going to be how can we maximize the separation between these electron pairs? How can we maximize the separation between these electron pairs, right? Okay, let's talk about the next one, which is BF3. Okay, let's talk about the next one, which is BF3. The structure is going to be like this. Three fluorines connected to boron, and obviously the lone pairs on fluorine to complete the octet. There are three bond pairs, right? So we have this boron, which is the central atom, which is having three bond pairs and zero lone pairs, right? Zero lone pairs. So again, a total of three bond pairs. As we are looking at the picture, this is the shape it is going to acquire. 120-degree angles from each side. So we are going to have this boron in the middle, chlorine, fluorine, and fluorine. Every angle is 120 degrees. Okay. Every angle has to be 120 degrees. Okay. This is called this is called trigonal planar. Okay. This is called trigonal planar. Fine. And why are we keeping it at 120? Because that's the best way of keeping these bond pairs at maximum separation from each other. Okay. Now let's move on to the next one, which is going to be CH4, methane. Methane, when we draw the structure, it becomes like this: C, H, 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 and H. This is the dot and cross structure. Again, if you don't know, you can see the video. Link is there in the description. But how should we make it to make it the most stable? How should we decide the shape? Here's the shape on the right hand side. We draw a tetrahedral. Okay. Now some students think that can't we draw it like 90 degree, just like we did 120s here for three bonds? No, because there's a better method of doing it. The better method of doing it is making it a tetrahedral so that every angle is 109.5 degrees. Every angle is 109.5 degrees. That is like more separation, more distance between the bonds, so they repel less repulsion. Okay. So that's tetrahedral. How do we draw it on a 2D paper like this? Carbon, hydrogen, hydrogen. Now this bond which is going inside, the bond which is going inside is drawn using dashed bonds. Okay, these are called dashed wedges. Okay, and the bond which is coming outside, see towards you it is coming. That is drawn like this, a solid triangle. You can color it as well. You like being artistic. This is how we should be drawing a tetrahedral in two-dimensional. Okay, it's a three-dimensional. Every angle is 109 degrees, right? So it's a tetrahedral and the bond angle is 109.5 degrees. Okay, I hope it is clear. When we have four electron pairs, we are going to draw a tetrahedral. Okay, let's move on to the next one, which is PCl5. When we draw PCl5, we are going to have 5 chlorines bonded to phosphorus with like 3 lone pairs on each chlorine. I'm not like helping you draw this because it will take a lot of time and elongate the class for no reason. This, there is a video for it. You can just watch it and learn it if you don't know. But it's a very easy structure actually. The best way to do it is the way it has been shown here. This is your trigonal bipyramidal shape. Trigonal bipyramidal. How do we do it? We do it like this. See, there is a phosphorus in the middle. We have chlorine, we have chlorine, we have chlorine, we have chlorine, and we have chlorine. Okay. So three in this 120-degree angle, one perpendicular on top of the plane, and one perpendicular bond below the plane, right? Like this. Um, if we have to draw in 2 dimension, so it will be like this. Dotted bond to show it is going inside, triangle to show it is coming outside, chlorine, and then chlorine and chlorine. This is how we should draw it in 2 dimensions. Okay. Now bond angles are very important. Bond angles. Let's study the bond angles here. If I just try to replicate, it is looking like this actually, right? So there are like two kinds of bond here. These bonds which are like in the plane, these are called equatorial bonds. Okay. E stands for equatorial. E stands for equatorial. Okay. And then this is A, which is called axial. Okay. E stands for equatorial and A stands for axial. These are the axial bonds. Okay. So different bond angles are there. The bond angle between axial and axial, as we can see, it is 180 degrees. Between equatorial and equatorial, we can see it is 120 degrees. And every axial is perpendicular to the equatorial. So axial equatorial is 100 and, sorry, not 100, it's 90 degrees, right? It's perpendicular, okay? So TCl5 is trigonal bipyramidal, and we have already seen the reason why. Okay, let's move on to the next molecule. The next molecule being the final one in our syllabus of international boards, SF6. Okay, how does it look? It look exactly what we expect it to look. 6 fluorines are bonded to it, each fluorine having like 3 lone pairs. Each fluorine having 3 lone pairs. Okay. How do we draw it? The best way of drawing it is this. It is an octahedral. Octahedral. Okay. Octahedral it is. And let's fill it out. Sulfur is there in the center. And then there are fluorines bonded to it. Okay. Fluorines bonded to it. Okay. So here it is. And how do we draw it in the 2D? That's important thing. So sulfur and then dash and dash to show that these two bonds are going inside the plane. SF, I'm talking about these two bonds, right? Going inside. And then coming outside, two of them, fluorine and fluorine. I'm talking about these ones now. And then there are two perpendicular bonds, which are fluorine and fluorine. This is how an octahedral looks in 2 dimensions, right? So bond angles again, bond angles will be obviously 90 degrees as we can see and 180 degrees. Okay, fine. So yeah, these are the 6 shape or electron geometries which are there in our syllabus. Okay. These were the easiest example where we are able to see what the shape is, and none of these molecules involved lone pairs, right? That was one thing. So these are the 6 examples without any lone pairs. Now we are going to decide what if lone pairs are present. Okay, what if lone pairs are present? Okay, so let's have a look. What should we do here? So when lone pairs are present on the central atom, the electron geometry the electron geometry. Electron geometry is the same thing we have discussed here. What should be, or how should the structure, like the shape, look like? Electron geometry is decided, and then we exclude the lone pairs to decide the final shape. Okay, to decide the final shape. Okay, let us see it with an example. Okay, the example is ammonia NH3. It's very important now. These are tricky questions which students get wrong. So you have to be focused here. Just keep listening. Okay. So this is NH3. Structure obviously looks like this. There are three hydrogens bonded to nitrogen and then a lone pair. Again saying, if you are not confident about drawing these dot and cross or structures of covalent compound, I've put a link in the description. You can watch that video. It's a short 20-minute video and you will learn everything about drawing structures there. Okay. So no worries. Now, here we have the central atom. We have three bond pairs, three single bonds, 1, 2, and 3. And then we have one lone pair, right? We have three bond pairs and one lone pair, correct? So that makes four actually, right? Total four electron pairs are there, right? Total four electron pairs. Now, what is the geometry for four electron pairs? That's a tetrahedral, right? For four electron pairs, it's a tetrahedral. So we'll draw a tetrahedral. That's the first step. We have to draw a tetrahedral. Let's draw it. So nitrogen, and then tetrahedral looks like this. N, H, 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 and then there's a lone pair, correct? This is how a tetrahedral looks, right? And what did we say here? We exclude the lone pairs to decide the final shape, right? We exclude the lone pairs to decide the final shape. Okay. So we're going to exclude it. So now it's going to look like this. What is happening? Just give me, we'll fix it. Okay. N, then H, H, and H. Okay. The top part, the lone pair is gone. Now it looks like what? It is looking like a pyramid. See, it does look like a pyramid. To join all these three, it does look like a pyramid, right? Triangular pyramid. So ammonia is the pyramidal in shape. Okay. Ammonia is pyramidal in shape. Okay. So that is the difference. It is not tetrahedral. Tetrahedral is the electron domain geometry. But if we remove the lone pair, if we exclude the lone pairs, it looks like a pyramid. So it is pyramidal in shape. Okay. Now remember that repulsion thing we discussed? The repulsion thing. Lone pair used to repel the most, then lone pair, and then bond pair, correct? So we're going to use it here. This lone pair is going to repel these bond pairs because that's what they do. Lone pair, bond pair repulsion is stronger than bond pair. So these bond pairs have to come closer to each other, right? They're going to get squeezed because the repulsion from the lone pair is too much. Repulsion from the top, the lone pair is much stronger. And that is why the bond angle, which should have been 109.5, decreases from 109.5 degrees to 107 degrees. Okay. So this is a very important point. Always they keep on asking in MCQs paper one that what is the bond angle in ammonia? It is not 105 degrees, rather it is 107 degrees. Okay. Is that clear? Okay. Now we're going to move on to the next one, which is the next molecule, which is water, H2O. So when we decide the dot and cross, it looks like this. Two lone pairs and two bond pairs. So we have two lone pairs plus two bond pairs, which is four. Four electron pairs, correct? So four electron pairs means it is going to be tetrahedral again, right? Tetrahedral again. So, oxygen, hydrogen, hydrogen, lone pair, and lone pair. So I've drawn a tetrahedral with two lone pairs and two bond pairs. Why is it tetrahedral? Because four electron pairs are there, and four electron pairs basically is a tetrahedral geometry, right? Now excluding the lone pairs, same steps every time. So O, H, H. This is how water looks. This is called bent shaped. So water is bent shaped molecule. Okay. Again, the repulsion is going to be there. So again, the bonds are going to get squeezed, right? The bonds are going to get squeezed. If to understand it better, let's make a lone pair like this. So they're going to repel each other. And because of that, the bonds are going to get squeezed together, decreasing the bond angle again. So this time, because there are two lone pairs, bond angle, because there are two lone pairs, bond angle decreases from 109.5 degree. 109.5 degree, it should be to 104 degrees. So 104 or 105, both are fine. Bond angle decreases from 109.5 degrees to 104 degrees, right? So that is what the changes take place. Water, the electron domain geometry is tetrahedral, but the shape is bent shaped. Okay? Okay. This is electron domain geometry. It's tetrahedral, but when we decide the shape, we have to exclude the lone pairs, so it will be bent shaped. Okay. Now let's see another example quickly. Another example is ClF3. Okay, ClF3. When we draw it, it is going to look like this. 1, 2, 3, 4, 5, 6. And then two lone pairs. So total of 5 electron pairs are there with central atom. If you check, 3 bond pairs plus 2 lone pairs, total 5 electron pairs are there. If it is 5 electron pairs, it has to be trigonal bipyramidal. Okay. So let's draw a trigonal bipyramidal. But there is a rule that we have to follow, which I'm writing here. In trigonal bipyramidal, lone pairs are always kept at equatorial position. Okay, that's a rule which you have to follow. The reasoning for it is not in our like AS level or IBDP syllabus, so we'll not be discussing it. It's like done at in like when you go into the universities, you'll get the reason. But for now, we'll just learn that in trigonal bipyramidal, the lone pairs are always kept at equatorial position. Okay, in trigonal bipyramidal, the lone pairs are always kept at equatorial position. Fine. So let's draw it. So phosphorus in the center, no, not phosphorus, chlorine in the center. That's a central atom. Lone pairs are two of them. So I'm going to make it like this. First lone pair and second lone pair. I'm trying to draw a trigonal bipyramidal here. And then fluorine, fluorine, and fluorine. This is how it should look like. The electron domain geometry is trigonal bipyramidal, right? But remove the lone pairs. So removing the lone pair, it will look like this. Fluorine, F, and F, right? Fluorine, F, and F, and F. This is called T-shaped. So ClF3 is a T-shaped molecule, okay? The electron domain geometry is trigonal bipyramidal, but the shape is T-shaped, okay? The shape is T-shaped, okay? I hope you're able to understand. Next, we have SF4. So SF4 is obviously sulfur 4 fluorines, and then there are two lone pairs, okay? So total, when we talk about the central atom, which is sulfur, we have 4 bond pairs and 1 lone pair, not 2 lone pair, it would be just 1 lone pair. So 1 lone pair. Again, making it 4 plus 1, 5 electron pairs, right? Again, making it 4 plus 1, 5 electron pairs, okay? Now, Again, trigonal bipyramidal, we are going to draw because it's 5, but lone pairs will be kept at equatorial. So we are putting the lone pair at equatorial and drawing the remaining bonds. This is your trigonal bipyramidal. Geometry, not shape. Electron domain geometry. This is the electron domain geometry. Now to decide the shape, we have to remove the lone pairs. We have to remove the lone pairs. F, 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 and F. And this is how it looks like. Now, how does it look like? And that's a very interesting thing to understand here. To understand what does it look like, you have to rotate it, okay? So S, F, 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 and F. What does it look like? Students, I think you all might have seen this. Like these are present in parks and amusement and like with kids play and they just do this up and down thing. This is called a seesaw, right? So this is a seesaw shaped molecule. So SF4 is a seesaw-shaped molecule, okay? And this is a process. Like whenever lone pairs are present, we will decide the electron domain geometry. From the six we have learned, linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, or octahedral. One of them will be the geometries, and then we'll exclude the lone pairs, not consider the lone pairs to decide the shape of a molecule, okay? And this process will give you the shape of any molecule. Fine. So that is what it is. Now I'm going to give you some questions for practice. Okay. So, and you can answer me in the comment section. Okay. Comment section. Decide shape and the electron domain geometry. Both. We have to decide the shape and electron domain geometry for both for the following molecules. Okay. I'm giving you three questions. First is XEF2. Second is XEF4. Okay. And there's one more third, which is SO2. Okay. These three questions I'm giving you. Comment the answers, obviously, the shape and the electron domain geometry. Let's see how many of you got it right. I hope you understood how to decide the shapes and electron domain geometry of all these molecules, which we discussed. Initially, we did the cases where there were no lone pairs, and then we did the cases where lone pairs are present, right? So once lone pairs are there, we have to remove the lone pairs to decide the shape after deciding the geometry. Okay. No questions will come out from this, whatever molecules we have discussed, plus these three. If you're able to understand all of this, you will be able to solve questions in the paper. Okay. Now, in the next class, we'll be discussing more things like how to calculate hybridization, how to decide polarity, and all of those things. You will understand everything very clearly. You just have to keep focusing, keep practicing, just try to practice some questions after watching my classes, okay, but after watching my lectures, okay. So yeah, that's it for today. Hope you understood everything. And let's meet in the next one. Bye bye.